All right. Well, let's make sure that this is running before I go too much further. Really appreciate anyone that's jumping on immediately. And you know what? It's okay if nobody jumps on because I'm doing this for me. I'm not necessarily doing it for anyone. I hope people benefit from it, obviously, but I'm doing this because I enjoy it. I am not a content creator. But I do like teaching and I do like explaining. I like the sound of my own voice sometimes, which is kind of beneficial. Maybe that is all a content creator is, honestly. Anyways, welcome to tonight's stream. I don't know if I'm going to do this twice a week, but we'll see there. Today, I am focusing a little bit more on some basics of Rust and AI programming, particularly GOAP or goal oriented action planning, and then the Rust trait system, because that's going to be very beneficial as we go into dealing with dealing with this particular system and any system really. First, I want to say thank you to anyone that's watching and anyone that has subscribed. It was kind of a weird feeling to see people actually enjoying the video and subscribing. Really appreciate it. Um, Let me know what the best parts are, the interesting parts are to you, um, because I would love to focus on parts that people enjoy and help people out here. With that being said, I don't know how long today's stream is going to go. One of my favorite streamers, John Gingset, very prolific Rust streamer, does like 4 or 5 hour live streams where he goes over Rust crates and just intense code. He's by far one of my all time favorite streamers. Um, I don't think I can get up to that same level. Anyways, today we're going to start out talking about about goal oriented action planning, a particular frame of AI planning. Now, goal oriented action planning is one of the, I would say, major methodologies for AI programming in games. Another very popular one is behavioral trees, and then utility UI, and then just the standard finite state machines. I'm not going to spend too much time on explaining the other ones or going into the ins and outs of why you would use behavioral trees versus other things. I will focus on why I think goal oriented action programming is the right choice for our simulation, however. So goal oriented action programming is very, very simple, I think. Let me get into a whiteboard here. I changed the whiteboard software which we're using. Draw.io just wasn't cutting it for me. So let me do, there we go. We're in Excalidraw now. And I will try to make sure that this is as large as possible. So goal-oriented action programming is, and one of the most important things I think about it is that it allows for emergent behavior. And what that means is where things like behavioral trees and finite state machines produce a very rigorous set of states or set of behaviors that AI can let's see, can exhibit or move forward. The goal oriented action planning is typically more of a reactive system or a hands off system. So let's talk a little bit about it. It's a very simple system. And now please understand that I am still learning this as well. I have done a few toy systems, but I am by no means a game developer. So we are learning this together. If you notice anything that I am wrong on or did not fully understand or explain correctly, do not hesitate to reach out and correct me. I'm all for that. So let's start with it. The idea is that you have a queue for your let's just call it an NPC, your entity. And in that queue, you have a set of goals. So we're going to call this goal one. We'll just copy and paste that. Of course, it didn't copy and paste all of it because why would it? Okay, let's just do this. Goal one. And it's actually let's give him better names than goal one. Let's do um we're not going to do attack player. Let's say let's make this about us, right? Let's make this about real people. Goal one is to um we go to Maslow's hierarchy of needs here. Let's say goal one is to eat. Goal two is to find shelter. And then let's say, oh, now it copies the words. Let's say that goal three is to, um, let's see, what's a good one here? Let's just say make money. There we go. So goal oriented action programming is this idea that your NPC or your character at any one point in time has different goals that it is working towards. Again, um, these are overarching goals: eat, find shelter, make money, and that they're prioritized in the order by order of importance and what they are going to attempt to do first. So they're going to attempt to eat. If they can't eat, maybe they go to the next goal, find shelter. Maybe they go to the next goal to find money. But what you have to understand is that in order to get these goals right, you might and this is where you get more complicated goal oriented action programming. These are really high level goals, right? And so what you have sometimes in larger system is a breakdown of goals where they have a bunch of smaller goals. So this one might be find food, then it would be to cook food, right? And these are the sub goals. So we've broken these down into find food, cook food, and these are goals, right? These are still goals. We're not into the actions yet. Find shelter. Let's say, let's just keep those. Let's keep those ephemeral for now because I think we're going to focus here. So the way I've understood this is that once we have this list of goals, um, planning takes place, and what that means is that okay, now as the NPC, I realize, okay, my overarching goal is to eat food. It's spawned some sub goals to help us break it down, both in programmatically and normally. As to first, we have to find the food, and then we have to maybe optionally cook the food. Now, what happens is a planning agent, and in object oriented languages, what you'll typically see is you'll see an overarching action planner. And what that action planner's job is, is to look at how do you do arrows? There we go. It's to look at the goals. Let's move that a little bit. Reviews goals, and then it will um, pull from a list of possible actions. Do do do. All actions NPC. Let's do this. All actions NPC can logically do, or that we've coded in there to do, right? And then it combines these two things together in order to create a plan. And what that plan is a combination of these goals or of this particular goal, right? the goal it wants to get. And let's actually move this down to find food. And then the combination of actions that would need to happen in order to accomplish that goal. In this case, let's go ahead and say um, that in order to eat the food or in order to find food, we are going to do the following actions, or we have the following actions that we can do. We can. This is going to be something I'm going to have to get used to. Investigate. Uh, investigate area. Uh, okay. Once we've investigated, we can move. And then let's say that we can, uh, let's see, obtain or pick up or whatever you want. Okay. And so what we've done is we have created a plan. We said, okay, in order to find food for this NPC, we have these actions that are available for us. These actions will satisfy this particular set of goals. So we are going to plan out how to investigate the area, w- and hopefully, once we see something, move towards it and then pick it up. Now, this is like very this is happy path, right? This is okay. This is what we want to do. What happens when I can't investigate the area? What does investigate the area mean? Um, let's change that. Let's say look around. So what happens when we look around and we can't find food? Um, what if we look around and we don't see anything? So now suddenly we have kind of this branch of okay, if we look around and see something, we suddenly want to see something. We want to move and obtain and pick up, right? Now, if we don't see anything, uh, do do do, uh, no objects or what have you. Let's move that a little bit out. Then what do we do? We actually might do the same action. We might tell it to move in order, move to a new location and then loop back. So move, loop back. We might tell it to, we might actually even tell it to give up, right? We might say, hey, now if you are, if you are someone that's dealt in AI, this starts to look more like a behavioral tree. And honestly, behavioral trees and goal oriented action planning have a lot in common. What's different is that the way we code this, the way we program how this part works, how this planning system works, is different in goal oriented action programming planning programming versus the behavioral tree. In a behavioral tree, you would treat this as a series of nodes, right? And so we would have this as a series of nodes with lines connecting them that have conditions, right? So again, we get to this look around and we say, okay, we found food, go on to this path, this node. Okay, we haven't found food, we go on to this node, which maybe loops us back to node one. But you can do a lot of this via UI. There we go. Unity has a lot of this set up via its behavioral tree UI system. Sorry, not Unity, Unreal. Um, and it's very like node and graph based. Goal oriented action planning is a little bit different because instead of hard coding this tree and building, these nodes one by one, what you do instead is um what you do instead, sorry, apologize. Um, and this is where I'm still shady because I'm still implementing this. So again, please don't hesitate to correct me in the comments if there are any comments about what we're doing. Is how we program this is a little bit more emergent in the fact that um, we can weight these things, we can weight these actions, and allow the planner, I guess this case the NPC's brain, um, to choose what might have the best options. So let's say we have these actions that are weighted. Obviously, look around might be weighted higher than a move action because we want to look around and see first. Okay, if we look around and we see something, maybe we have an action that's changed to it. Okay, we've seen something, we've seen our food, um, a- and I think we move towards it. I'm still hesitant on exactly how we're going to implement this. But the idea here is that we're not hard coding a lot of this behavior. This move, this look around, this obtain and pick up, these are actions which are going to be very general actions. And we want to give the NPC AI tools, just like, if we had to look at LLMs or something like that, tools which it then can use to attempt to find this goal or to attempt to get this goal. And so what we do, I think, in the programming is that for this particular goal, we create a list of weighted actions that we can tweak and mess around with and assume will lead to this particular setup. So we'll say, okay, for the find food action, or sorry, for the find food goal, we assume that there's only 3 or 4 things you can do. You can give up, you can look around, you can move, um, and you can pick up, right? That's really about all you can do in order to find food. Maybe we add, like, buy food, and this is where we start to get really complicated. So now what we have is we have a weighted list of potential actions that the planner can choose from. And maybe it's as simple as, okay, we're going to go in priority order. We looked around, we didn't see anything. Okay, well, let's move on to the next weighted action. We'll move around and then we'll restart this plan and we'll say, okay, hey, I moved. I did this action. What action should I do next? Okay, well, let's go to the highest weighted action. Let's look around again. I don't see anything. Let's move. But I just moved. So we can put like we can manage the state. We can manage how many times we can in this loop do we do a certain action before we give up and break out of the loop because there probably needs to be a way to break out of that loop after a while to be able to see, okay, hey, we've looked around, we've moved a lot, we're still looking around, we're moving, um, we haven't found anything. What I think will end up happening is that the breakout of this loop doesn't have to be handled here. These actions in this plan, like they don't have to care about how many times this has been attempted. What does care is this portion, the goal planning, because now we can say, hey, we've been attempting to find food for 30 minutes. And suddenly the priority for finding food has dropped drastically. Suddenly it's nighttime, it's 10 below. Now suddenly, okay, hey, eating is no longer our top priority. Um, Now it's finding shelter, right? And so my assumption and how I'm going to attempt to program this in a simulation, especially, is that um, these actions have timeouts, or that the world can interact, or the systems around them can interact and modify the weights or the importance or priority of these goals in order to break out the actions. So that way, the actions themselves don't need to manage any state. They don't need to know how many times they've been tried. They don't need to know in what context they're being tried. The only thing that has to care about this overall is this guy, this action planner. And this action planner um, doesn't necessarily manipulate the goals. There might be, or sorry, manipulate the priority of the goals. There might be something that else that manipulates the priority of those goals. So that's kind of how I understand goal oriented action planning. Again, in behavioral trees, you would plan this entire potential thing out. They're very fast. They're very computationally inexpensive. Behavioral trees are. Whereas goal oriented action planning can be very computationally intensive depending on how many entities, planners, and things you're having to go at once. In a traditional object oriented game, this action planner is usually a um, a high level service or something along those lines, as is what I've seen before. And that high level service is interacting not only with the goal of one system, but many systems at the same time. In an entity component system, where we're doing a lot of things in parallel, my gut assumption and what I've seen from things like Caves of Cud and Dwarf Fortress is that we can do action planning and this whole move more cheaply than an object-oriented system can do. Because if you think about this, there's a system for the action planner, there's a system for the goal prioritization and the goal creation, and there's a system for the actual actions that are queued. And then there's a system for handling those actions and having that NPC interact with the rest of the stuff, right? Um, so give me just a second to take a quick drink here. Let me do before I go any further, because I think we're gonna jump into the next part, which is the rust traits here. Because I think in order to move forward with rust traits, do, 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 uh, da, da, there's okay. In order to move forward with apologies, my wife texted that she is going to bed, so I'm just saying goodnight. Um, in order to move forward with this plan, we're going to have to figure out how to encode this correctly in our game logic. And that's why I wanted to get into Rust traits today, because I think that's going to really benefit our patterns here. So let's go ahead and jump into our programming. For those of you that are interested, this is VS Code. It's the Microsoft run editor. I tried using VS Codium, but the extensions I use for Godot just didn't play super nicely with it. I'm going to try that again eventually. I would love to use. I was a big IntelliJ and JetBrains user for a long time. Unfortunately, there's no JetBrains product that allow you to do C sharp and Rust at the same time. Um, and then I was a Z user, but the C sharp and Godot extensions for VS Code are, I think, superior in the VS Code ecosystem than they are in Z. Um, and then prior to that, I'm still very much use Vim quite often, um, but with the onset of LSPs and all of this fancy material, um, I got really used to using IDEs and editors. That being said, I do still use the Vim key bindings. So just a bit of trivia there. So I have made sure I didn't commit these files so that you could see the new files that I've created here. So I've created one called AI, and the way I like to structure my Bevy system is I typically have any of my modules that handle behaviors split up into apologies, I thought I heard something. I have them split up into the entities, which typically you don't even need a folder for entities since entities are just like objects with IDs. That's all they really are. Components, which are the actual components we're talking about, and these are Bevy components, um, or anything supporting those components, and then systems, which are the actual systems um, that you would build in Bevy. Okay, we're not going to talk about systems today. I think that might be something as we continue on with this milestone one with player simulation and player walking and all that jazz. That we will add a system maybe next stream, depending on how far I get on programming this. So let's talk about Rust traits. I'm going to go into this assuming that you've had at least a little experience with programming languages, but I am going to try to keep it enough to where even if you're new to programming and coming into Rust, which good on you, Rust is not an easiest first language to attempt, but good on you. Um, but I'll try to keep it high enough level. So the idea here is that traits are very similar to interfaces or the idea of an interface. What that means is that you are describing a set of behaviors. That's it. Or a set of behaviors and potentially a set of attributes um, that can be applied to multiple different multiple different types. So if we look at a type, let's say, let's see, I'm not going to do type. Type's not the right one. Let's do pub struct. Struct is it's a struct. I don't know how to break that down further. It's been a long time since I've had to break that down further. You can think of it as structured data. Again, a struct. So let's call this test. That's that struct. Actually, no, let's call this an NPC. Uh, Actually, let's just call it. We'll keep it in the folder. We're not going to keep it here. We'll move it later. The NPC, let's say it has a name, which is a string. Oh God, do I remember even how to do this? Yes. Okay. Jeez. It's been a while since I've worked in Rust. I have been knee deep in Python and knee deep in Go. So please forgive me if I'm a teeny bit rusty with some of the original Rust syntax. Apologies. So we'll give him a name. Um, and then let's say we give him just a description, right? And then it doesn't look like I need. Yeah, it looks like I need commas. Perfect. Okay. So we'll give them a name and a description. In Bevy and in entity component systems, I would not assign things like location or other components that need to exist on this NPC here. This is like attributes that are very specific to an NPC. In object-oriented programming, an NPC node might inherit from a node with a location already, like a location in the map. But in Bevy, what we would do is we would let me double check on how to do Bevy components. It's been a little bit. Please forgive me. Yeah, okay, we have to derive the component. That's what I thought. We're not going to get too much into the derive here. Just note that what this does is that this gives us a lot of behaviors and lets us treat. Oh my God, if I could spell. Forgive me. Component. And we're going to say that this is another struct. This is a location, and we're going to call this a location in our game. And we're going to say pub x, which is let's do an F32, which is a float 32 bit, and y float 32. Again, we're 2D space here. And then I'm going to have to import that. Let me make sure that that is exactly what I want to. Yeah, import Bevy. Perfect. So that should get rid of that. Perfect. So what we would do is when we instantiate an NPC, which would be its own component, right? The name might actually be its own component too. Okay. Just keep that in mind. This might be nothing but a bare struct. And that's okay in entity component systems because we just need a way to differentiate this from another one and be able to query on it. So in reality, when we instantiate these, and by instantiate I mean add them as an entity in our game system, right? Um, what we do uh, is let's show you what it looks like in Bevy. We would do something like world dot spawn, and we would spawn an entity that is a combination of NPC, and don't quote me on the syntax here. Um, and let's say the NPC has a location component on it, and probably want to split out the name into its own component. Okay, and so when we spawn an entity, this entity is going to get its own UID, unique ID, and it's going to be what represents our NPC. We're saying, okay, it's an NPC because it's got the NPC component on it. That you can think of that as its type, but it also has a location component and a name component, and it might have tons of other components. Might have an AI component. It could have a inventory component. Okay, we're going to get into this all a little bit later. Don't let this distract you right now from the traits. Okay, just keep that in mind. So we're going to get rid of that. Let's get rid of this for right now, and let's get rid of the derive just to keep this easy. Okay, traits. Traits describe behaviors or attributes which can then be implied, I think is a good way of putting it, for a given struct. And what this allows you to do is take a struct and use it in a function whose signature or what expects something that's not that struct. So for example, what we can do, let's say we want to let's say a common one is we want to greet anything with a name, right? Um, ignore these for right now. Trying to think of a good way of putting this. Let's do this as a trait, right? I don't know that I can do. Yes. Oops. Yeah, I don't think I can do that on traits. Um, do. Uh, yeah, I'm pretty sure I can't do that. Do. Uh, uh, yeah, I just realized you cannot see my screen, can you? You cannot. Okay, I'm sorry, you cannot see that. I'm trying to get it to work here. Okay, anyways, let's go back to trait. Traits of behavior, right? So the behavior that we want to say that this NPC can do or uh, that it can implement is the act behavior, right? Um, let's change that. Let's do another trait. Let's say to trait um, greet, and what this is a function, and we're gonna make this a public function. That's greet. No, say um, name. Okay. And if you notice, we're not doing anything right now. We're not saying we're gonna give it itself as a parameter, and say that hey, anything that's got the greet trait has a function that says say name, and it's actually, let's say it returns a string because we want it to say its own name. I don't think it doesn't matter. Yeah, we don't need the pub. qualifier on that because the trait is public, so we don't need the public there. So what we're saying is that anything that implements this greet trait should have a function that is called say name. And the assumption we make from this, and maybe the comments here, is that it's going to say its own name and return its name as a string. Okay. And what we can do later on is we can actually write functions that says, hey, let's say we're going to call this our function. We'll call this a greet system. And what this system does is it should take an array, and we're gonna do NPCs first. We're gonna just call it NPCs, and we're gonna say, oh man, it's been forever since I've done this. We're gonna say that it is the NPC struct. Actually, we're gonna say it's a vec of NPCs. Oh my god. And if you're not familiar with vecs, these are very akin to arrays. I highly recommend you check out John Jeanset's video on data structures in Rust. It'll change your life. The greet system, all it does is it goes for, let's go NPC in NPCs, right? And it calls, it should, we're gonna say, we're just gonna print the NPC dot name. Okay. Probably because it needs to be a string literal. Uh, that is not gonna work. Okay. It has been a while. Print. Is this how we do it? God, it's been a while since I've done print. Oh, curly braces. Sheesh. That's what I just did was Go syntax. So you're gonna have to deal with me a little bit as I do through this. So what greet system should do is it will take an array of NPCs, it will iterate through each of those NPCs, and it'll just simply print its name. Now this is great for NPCs, but what if we had another struct? Let's say pub struct. Let's say this is the buildings. Actually, no. Let's keep this people. Animals. We'll say this is animals that also have a name string. Now, in order to greet animals or to have any of our systems be able to, have the animals print their name or say their name or do their anything, we have to write another function in order to um, do this. Because if I tried to pass an animal struct or a vector of animal structs into greet system, it wouldn't work. It'd give me a type error. It wouldn't compile because it's not NPC, and this is expecting NPC. Okay, that's a problem. What we need to do is change this function to, instead of expecting a stable struct, which is this NPC or this animal, instead of expecting a specific struct, we can instruct this function to say, hey, instead of expecting the NPC, I want you to inspect or expect an implementation of greet. Okay. And what this allows us to do is now, instead of calling that, we can say, say name. And that's probably freaking out for, nope, that didn't freak out at all. It's just my LSP's behind. So now what we've said is that, okay, this function accepts an array. We'll call it an array for right now. It's not, but we'll call it an array. This expects an array of any struct or any data structure or type that implements, and this could be any type. Keep this in mind, that implements this trait, the greet trait. Okay. And so as long as something implements the greet trait, we can say its name. Now, right now, neither an NPC or um, or the animal struct have uh, have those implementations, right? We haven't actually done any implementations. Just like a normal interface, we do have to we do have to actually code in what that implementation will be for the individual struct. And this should actually be very simple. We're going to say implement greet for NPC. And so it flows off the tongue really. And a lot of your IDEs will actually um, go ahead and let you implement the missing members. And so if you notice, in order to have this compile, I must have the same function as the trait with the same signature, which is just the self, which refers back to the struct, and then it must return a string. And in this case, the to do macro is going to break everything. But all we have to do now is we return self, or sorry, is it yeah, self dot name. That's it. That's all we have to do. Is that right? Oh, because we did a reference. We don't need it as a reference. We can clone it. I don't have clone implemented, so it's probably going to freak out. No, it didn't. Okay, that's fine. So what I'm saying is because let's actually just change that. That's going to confuse the crap out of everyone. We're not getting into borrowing today. Let's just say we take a copy of self and we're returning self name so that we're not dealing with any copies here. Let me take a quick drink. So what this means is now I have implemented greet for NPC. And if I implement greet for animals, impl greet for animals, oops. Oh my God. Animals, you can tell it's getting late for me. Um, it's going to give me the same issue. We're going to type it out by this time, func say name, and we're going to do the same thing, return self.name, because we have the same kind of thing. But what if this wasn't name? What if this was species? Well, that's easy. We just return species. And if you notice, the implementation is still valid. It still works because this part doesn't care under the hood what the struct is. As long as it implements it, and as long as it returns a string, it does not care where that string came from under the hood. And it doesn't care what this is. So now if we write another function, let's just write a test function where I can use this. And we say, let NPC equal NPC, and we have to give it a name, right? Is that what we have in there? Name test string, and again, this is a string type. Description test to string. Okay, so we have the NPC. Now, if I call greet system and I pass it in we're going to call a vec. This is the macro for it, so don't worry too much about it. This just allows us to create a vec on the fly. You can see that I'm not getting any compile errors, right? Because greet system expects as long as whatever's in this vector implements greet, this will work just fine. Now, this is probably going to really blow your mind. And I want to see this should work. We should be able to make a let vec, or sorry, let how we want to do this. I'm trying to remember let's say let test vec, and we're going to say that this is a vec, but we're going to say it's a vec of greet, right? Oh, that's not gonna work because we can't do it with a tree, 'cause then it becomes dynamic, duh. Okay, we're not gonna worry too much about that. I just wanted to see if we could do something cool. Anyways, so that works with that, right? And so if we do let animal equal animals, species, test, I don't care what it means or what it says right now, to string, and then I call greet systems, vec animal. Again, it works just fine because the animal implements the greet, the greet trait. If I remove the implementation of greet for animals, let's watch what happens. Suddenly I have a compilation error because greet is not satisfied for animals. Okay. So we have to have those implementations. Um, Now, this is where it gets cool because you can do this with other languages really easily. These are interfaces, right? You can accept an interface in a function and return an interface um, in a function. But this is where it gets really cool. What we can do in Rust is we don't have to be bound by a single trait. We don't have to implement one trait. So let's say there's another trait here that's action, right? Um, we're going to change the function signature of this, and don't get too alarmed. This is a generic. Okay. We're going to change this into a generic function. This is another way to do the exact same thing we were doing. Greet. And instead of impl greet, we just do T. Okay. What this nomenclature is it's the same thing, just different. And if you go into the Rust book, it'll run through the same thing for you. But basically what we're saying is like, again, we're taking a generic type. We don't know what the type is, but we know it implements the greet trait. And um, and then this is where that type is being used, and the type being used here. What was that? Okay, sorry, I thought it was a bug. But what's really, really, really cool is that in Rust, I can say it doesn't just need to implement the greet trait. We also need to is it the action trait. We also needed to implement the action trait. And so if you notice, this greet system now is different because in order to have this work, this type has to not only implement greet, but it has to implement action as well. And if we scroll down to where we're at, it looks like the LSP is going to stop at the very first one. Greet system's not going to work because NPC does not have the action implemented for it, right? So now we have to go back and we say implement action for for NPC, and then we have to do function act, and let's just this does nothing but return. Okay, that's all it does. But now you can see that we what did I mess up here? Impl action for NPC, impl greet for that is creates greet and action greet system. What is going on here? Oh, that's because um it's probably this vec that's freaking out here. So let's change that. So let vec or let test we're gonna say this is a vec of NPC equals vec NPC. Does that fix that? NPC action. Oh, that's because is that not what I need? Holy cow, it's been a while. Let me make sure that I am not insane here. Now, if you notice, this is a very common occurrence for programming. Um, unless you're using AI that just does the whole thing for you, and then you're learning nothing, in my opinion. But I just have to remember do how I did this correctly, what I'm messing up. Oh, that's why. There we go. Because I was using the wrong I was using a comma, which is a little bit different. So the plus is what I'm saying. It's like, okay, it has to be greet plus action. The comma there would be greet or well, I believe it's almost a greet or action type, or it has to be anyways. What this means is it has to implement both in order for that to work. And if you notice that suddenly, oh hey, NPCs now functions correctly, and animal is broken because again, that is not implemented for animal. Okay, hopefully that makes sense. And I know we're kind of getting to the wire here um, with this. This is if you don't get this right away, that's okay. I highly recommend you check out the Rust book and go into the traits in the Rust book. Just do Google learn traits Rust, and it'll be like the first link you hit. And I'll try to put this in the show notes. But the big thing to understand is that traits are extremely powerful because it allows us to start combining those. And we're going to need that as we go into goals and actions to combine systems and not have to rewrite that for everything that needs to have AI. Okay. I don't want to keep you too much longer. It's been almost an hour. I can't believe I actually have done this for almost an hour. I can see why and how easy it is to go on. I want to say thank you. Really appreciate you coming in. Really appreciate you watching this video. Again, I hate saying it, but like and subscribe. If this is helpful, let me know. Let me know if you need to know something else that I can help with. Let me know that too. More than happy to help. Thank you. Really appreciate it. I'm excited to actually show you something next time of how we've used traits to implement this. I'm trying to find that good balance of let's teach aspects of programming and Rust and Bevy and Godot, but actually implement and build a game at the same time. So help me find that change. Thank you.